In the last lecture, we defined Jp to be the lattice of order ideals of a poset P. In this lecture, we'll compute the Mobius function of Jp. So given two order ideals I and k in Jp such that I is contained in k, we want to compute mu in Jp of I comma k. And this we know is just the mu in the interval between I and k of 0 hat and 1 hat. The least element of this interval is I and the greatest element is k. And now the calculation becomes simple if we just realize that this interval itself is of the form, is the lattice of order ideals of some poset. And that's that this interval I comma k in Jp is isomorphic to the lattice of order ideals of of k minus I. And this is not difficult to prove. Given ideal L here between I and k in Jp, you just map it to L minus I. And given an order ideal here, let's say L prime in k minus I, you just map it to L prime union I. And these will define mutually inverse functions from each of these sets to the other, thereby proving that it is a bijection. Now for this Mobius function to even make sense, I need that this interval is finite, and so I'm going to assume here that k minus I is finite. Well, I guess right up here. And so now my problem is reduced to compute mu Jp 0 hat 1 hat for any finite poset P. For this, we will use Weisner's theorem. Recall what Weisner's theorem says. It says that mu Jp 0 hat 1 hat is equal to minus sum over. So we'll have to fix any ideal A which is properly contained in P. So any element of this poset which is not equal to 1 hat. So then we have to take here I non-empty order ideals and I intersect A is empty. Mu Jp I comma 1 hat. So that's the statement of Weisner's theorem adapted to Jp. What shall we take for A? So let's take the first case. Suppose there exists x strictly less than y in P. So this just means that P is not an antichain. Now if P is not an antichain, then I can assume without loss of generality, since P is finite, if x is strictly less than y, I can replace y by some element that is maximal. So y a maximal element of P. Then I can take A to be P minus singleton y. This is an order ideal whenever y is a maximal element. And if I intersect A is equal to the empty set, then this is the same as saying that I is contained in singleton y, which leads to two possibilities. Either I is the empty set or I is singleton y. But this is just the 0 hat, so this does not appear in this sum. I equals y is not possible because singleton y is not an ideal, because we have x which is less than y, and that's not in the singleton Y. So this is not an ideal. And so the sum here is the empty sum. We have mu jp 0 hat 1 hat equals an empty sum which is 0. Now the only other case is that P is an antichain. In this case, Jp is just 2 to the power P, the power set of P. And we already know the Mobius function for this partially ordered set. We have mu Jp of 0 hat 1 hat is minus 1 to the power cardinality of P. So the upshot of all this is that mu Jp of I j is equal to minus 1 to the power cardinality of j minus I if j minus I is an antichain and 0 otherwise.